title of my talk is Multilevel Methods with Inexact Solver on the coarsest level. And I will start with a brief introduction to the multilevel methods. Then I will explain why we are considering using inexact solvers on the coarsest level in the multilevel methods. And afterwards, I will describe the two topics or problems we are currently trying to solve. Firstly, I will talk about deriving stopping criterion for the solver on the coarsest level. And secondly, I will discuss the usage of recycled Krylov subspace methods as the solver on the coarsest level. So let's start with a basic terminology. In the literature, you can find multilevel methods and multigrid methods. Multilevel methods is a more general class of methods. Today we will focus on multigrid methods. And then we distinguish between geometric and algebraic multigrid. So I will start with geometric multigrid and then explain the difference. So as a model example, we will consider the Poisson equation on a unit square on a domain omega, and we will consider homogeneous Dirichlet boundary conditions. Here we have the equation written in a weak form. And as a model example, which I will use throughout the talk, we will consider the peak problem, whose solution is plotted in here. And since we are in Dublin, we can also call it a spire problem. Okay, so we will discretize the Poisson equation using continuous Galerkin finite element method. We consider a triangulation of the domain omega, and we are searching for the approximate or discrete solution in the space of continuous piecewise linear functions, piecewise linear corresponding to the triangles. And we are searching in a space of functions which are vanishing on the boundary in order to include the boundary condition. And a function which equals 1 at a certain node and 0 at all the other nodes, and it's piecewise linear. It's called a nodal basis function or a tent function. And we can use these functions to, and these tent functions form a basis of the space Vt, and we can use them to reformulate the discrete problem of finding a function which satisfied this equation into a problem of finding the coefficient, the vector of coefficients u of the function in the nodal basis, and then the coefficient vector satisfied system of linear equations with sparse, symmetric, and positive definite matrix. So geometric multigrid methods discretize the problem on a sequence of levels. Here we consider a sequence of uniformly refined triangulations. That means that each triangle is divided into 4 congruent triangles. And our goal is to solve the discretization, the discrete problem on the finest level. The V-cycle method computes the approximation using smoothing on fine levels and by solving a system of linear equations on the coarsest level. Now I will explain it in more detail with illustration on the peak problem. So let's start with some approximation u0 to the solution u. Since we have no prior information, we will take it to be 0. And for a 0 initial approximation, the exact solution and the error are the same. so we can plot the error. And first, in the V-cycle on the fine level, we apply smoothing. The smoothing should have the effect of eliminating the oscillatory parts of the error, and it usually consists of a few iterations of a stationary iterative method such as Jacobi, Gauss-Seidel, or SOR method. And after the oscillation parts are eliminated, further smoothing iterations are less effective, and we will approximate the smooth parts of the error on a coarser level. We move to a coarser level by computing a residual and projecting it using the restriction operator. And the restriction operator is defined using the finite element schemes and it corresponds to the geometry. So on the coarser level, we are solving. On the coarser level, we take the projected residual as the right-hand side, and we are trying to find the error so that we can later project it back to the fine level and correct our current approximation there. Now we can view it as a separate problem and again consider a zero initial approximation. And now if we look at the error of the problem on the coarse level, the error again has oscillatory parts, so we can apply smoothing. And after the error is smoothed, further iterations are less effective, so we again compute the residuum and move to a coarser level. On the coarser level, in classical multigrid methods, the problem is solved by a direct method that's based on LE decomposition. Today we will also assume that we will also allow inexact solvers. So we assume that we compute just an approximation to the solution E. So after we have the approximation, we can project it back to the finer level and correct our current approximation there. The projection is done by projection operator, which is again associated with the finite element scheme. And this process is repeated until we reach the finest level and correct our approximation there. So this was one iteration of the V-cycle method, and usually we apply a series of iterations. Sometimes the smoothing is also used after the correction, and it has an effect that the operator which corresponds to the application of the V-cycle is symmetric. Okay, now as an aside, I will explain the difference between geometric and algebraic multigrid. So in the geometric multigrid, we have a continuous problem, and we discretize it on a sequence of levels. And the matrices A2, A1, and A0 corresponds to the discretization of the problem. And the restriction and prolongation operators between the levels corresponds to the, or are defined using the finite element scheme. So there is a notion of geometry. In algebraic multigrid, there doesn't have to be any geometry. It is a method for solving the system of linear equations, and restriction and prolongation matrices are defined based on the properties of matrix A. The coarse level matrix is defined using the restriction and prolongation matrices and the original matrix A. Okay, now back to the geometric multigrid, since A is symmetric positive definite matrix, it defines a norm. This norm is called an A norm, and from the physical point of view, it corresponds to the energy in the system. The V-cycle method the convergence of the V-cycle method in our setting is studied, for example, in an article by Iserentan from 1993, and we have a theorem that under certain assumptions on the triangulation, restriction, and prolongation operators on the smoothers, and what is important, provided that the problem on the coarsest level is solved exactly, there exists a factor μ, which is independent of the number of levels and of the size of the problem on the coarsest level, such that the A norm of the error is after each iteration reduced at least by the factor μ. So this result of this is called a uniform convergence. The uniformity is understood with respect to the number of levels and with respect to the size of the problem on the coarsest level, and μ is the bound on the rate of convergence. The problem with this theorem is that in practice, when we are solving large problems, the size of the problem on the coarsest level can be so large that we are not able to use direct methods based on LU decomposition or Cholesky decomposition, and thus we cannot use this theorem in practice for practical situations. And so if we have a large coarse level problem, we can start with a coarse triangulation and just have a V-cycle method with more levels. So this can be easier done in our model example, but this approach of reducing the size of the coarsest level problems cannot be used in problems with complicated geometry. For example, if we try to gradually coarsen this mesh, the circle would be approximated by polygons with less and less edges, and eventually we would lose some information about the geometry of the problem. So another example where it is not advisable to have really coarse grids is when we are using parallel computations. And in parallel computation, the nodes or the degrees of freedom are associated to different processors, and the processors run the computation in parallel, and they are communicating with each other. So on the fine levels, each processor has lots of unknowns, so the computation part takes a lot longer time than the communication. But if we move to a cursor level, the number of nodes associated to one processor decreases, and so the computational part is now fast, and the communication part is also decreased, but not so much, since we still have to communicate with other processors and we have a latency. So it is not advisable to have really coarse grid, and it is better to have a triangulation with more degrees of freedom. So in problems where we are not able, when we have on the coarsest level large problems and using LU decomposition methods is ineffective or even prohibited by the size, it is natural to use inexact solvers. We can use a different variety of them. For example, solvers based on incomplete Cholesky or LU decomposition, or on lowering approximation of the matrix, or we can use iterative solvers such as stationary iterative methods or Krylov subspace methods. So if we are using iterative solvers, there are new problems which we have to deal with. For example, where should we stop the solver on the coarsest level? So the most basic stopping criterion is the relative residual stopping criterion. And the question is, which tolerance can we choose? Should we choose? So we can run a numerical experiment. We consider the peak problem with the V-cycle method with 2 levels. The smoothing on the fine level is done by 3 iterations of SOR. And we consider 4 different variants of the solver on the coarsest level. MATLAB backslash is a direct solver, which is exact up to machine precision. And then we consider CG with the conjugate gradient method with the relative residual stopping criterion with different tolerances. So here we see the A norm of the error and how is it decreasing when we apply the V-cycle iterations. The black, yellow, and purple line are the same line in here. So we see that if we have really high tolerance, then we see a significant slowdown. And for the second tolerance, 10 to minus 1, the method is slower in the beginning, but then the rate of convergence is nearly the same as for the variants with the second and with the third and fourth tolerances and with the MATLAB backslash operator. You can also look on the total number of iterations performed on the coarsest level. And there are 2 interesting observations. The first one is that the winner in the sense of doing the least amount of iterations is the conjugate gradient method with the tolerance 10 to minus 1. And so we have a method with inexact solver, which is slower than a method with exact solver in the beginning. But in the end, it needs to do only 1 additional iteration than the method with exact solver. And I should have said in the beginning that the methods were stopped when we reached the level of attainable accuracy at the level 10 to minus 14 for this problem. And like second interesting thing in this experiment is that from the comparison of the CG with the relative tolerance 10 to minus 2 and 10 to minus 3, we see that using higher tolerance, 10 to minus 3 does not create like much more accurate things. And for this problem, using the tolerance 10 to minus 2 is nearly the same as using the exact solver. So the questions we are interested in are how to choose the relative tolerance. More generally, is relative residual stopping criterion the right one to use? And if not, can we derive a stopping criterion so that the method converges nearly the same as the method with exact solver, and we do minimum amount of work. So using or having a good stopping criteria would can significantly reduce the number of work we are doing on the coarsest level. And another way how to reduce the amount of work is to use recycling. So on the coarsest level, we are solving throughout the recycle method, we are solving systems with the same matrix, and only the right-hand sides are changing. And the idea of recycling is to reuse an information obtained when solving the first system to speed up the solution of the second system, and so on. So now I would like to show an experiment with the restarted GMRS method and its recycled version GCRODR. Here the recycling is based on computation of harmonic grid vectors. So we consider the same setting as before, and here we can see the number of matrix vector products the method needed before stopping with the relative tolerance 10 to minus 2 in the V cycles. So in the first V cycle, the number of matrix vector product is the same, but the GCRODR saved some information. So in the second run, it required the half of the matrix vector product than the CG. And if we look at the total number of matrix vector products performed on the coarsest level after 16 V-cycle iterations, we see that GMRS needed nearly 3 times more matrix vector products. Okay, so we are studying different recycling strategies, and we are trying to find out whether there is a best recycling strategy for the solver on the coarsest level in multigrid methods. Okay, so that's all. Thank you for your attention.